Alright, welcome to lesson 1.1. We're going to continue looking at these examples. So this is class example number 6 in your book. It's a class example of the Pythagorean theorem, c squared equals a squared plus b squared, where we're trying to find the length of our hypotenuse right here. So if that's our hypotenuse, then we want to determine the exact length of this line segment from here to here, or here to here. And we want to express our answer in simplest radical form. And so the reason we want to express it in simplest radical form is because we want to know the exact length. We don't want to plug something into our calculator with the square root and get a decimal answer. And so if we look at what the triangle looks like that's going to be formed, it could look something like this. Since that's just giving my hypotenuse, I could go the other way as well, but it's a little more intuitive, maybe, if we think of it like this. So there's my triangle, and we know what Pythagorean theorem is: c squared equals a squared plus b squared, or a squared plus b squared equals c squared. In this case, what we're going to do is we're going to use these variables we're given. So we're given AB, and that's what we're looking for is this side AB. So we're going to say AB is equal to, AB squared is equal to, we'll call this A, and we'll this side B. A squared plus B squared. And A squared, if I look at the number of grids, I know it's on this coordinate at -6 and -2, and B is at 3 and 1. But the actual number of squares that represent this line from A to, I guess this would be C, would be 1, 2, 3, 4, 5, 6, 7, 8, 9. So AB squared is equal to 9 squared plus, and the side B, 1, 2, 3, 3 squared. So then what we're left with is AB squared is equal to 81 plus 9, or AB squared is equal to 90. Now remember, just like if we were to plug into Pythagorean theorem, which is what we're doing, but if the version you're kind of used to, right here, after you find out that value, that gives you c squared, just like I have AB squared. And so in order to get AB, we're going to have to take the square root of 90. Now remember, I don't want a decimal, right? I want the exact number, the exact value of this radical. And so if we were just to type it in like this, that's not an exact value we're given, because we're going to have to round our final answer to probably the nearest 10th or 100th. And so if I'd round it, it's not an exact number that I'm giving, right? There's decimal places that I'm leaving behind. So what we need to do is what we were doing in the previous examples, and we need to find out what the largest perfect square is going to be, which is going to be 9 times square root of 10. And so then my exact number, square root of 9, that's a perfect square, is 3. Square root of 9 is 3 times the square root of 10, and that is my exact length of my hypotenuse. 3 times square root of 10. Which, if we think about, so square root of 90 would have given me my value, if we think of that in centimeters, for example, 9.48 or 9.49 centimeters. 3 times square root of 10 is going to give me the exact same thing. But this is more exact. We can also represent this using the distance formula. And the distance formula is given to me as d is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. So these x2, x1, y2, y1 values come from the actual coordinates. So I'm going to highlight those in blue. So my actual coordinates were at point A, -6 and 2, and point B, 3 and 1. And so those are the values I'm going to plug into my x and y values here. And so my distance is equal to the square root of x2, which we could say 3, minus x1, which was -6, so it's actually going to be plus 6, squared, and we're going to add my y2 values. So y2 is 1, and y1 is negative 2, so it's going to be plus 2. So we have a double negative there. So if we simplify that, the square root of, well, 3 plus 6 is 9 squared, plus 1 plus 2 is 3 squared. If you look up here, we're ending up with the same thing, right? So square root of 81 plus 9, or square root of 90, or we have the square root of 9 times square root of 10, which is going to bring us to our same answer of 3 times the square root of 10. Alright, so both times we end up with the exact same thing. Now, what we've been doing is we've been converting entire radicals into mixed radicals. But how do you go back? So mixed radicals into entire radicals. So we know that every mixed radical can be expressed as an entire radical, right? Like 3 times square root of 10 is square root of 90. Right? That's how because we went from square root of 90, an entire radical, to our mixed radical. So what would that look like? So complete the following to convert 3 square root 7 to an entire radical. And the way that's done is you raise the outside number. So in this case, my outside number is 3. So I raise that to whatever power is represented in the index. Right? And so remember, this is the index here. And if you have just a square root of 7, the index is 2. So if I raise this outside number to the index as an exponent, which would become 3 squared, I'm going to be left with 9 inside of my radical sign. And that is the same thing as 9 times 7. Or 9 times 7 is 63. That's my entire radical. Alright, so what you're doing, you're thinking about, well, what did I have to, what's the number 3 squared? That would be 9. And so if you look at the other way, what is the square root of 9? Well, it's 3. So what did I have to do to square root the previous number to get this answer? All right, so let's look at a couple more examples. So a mixed radical of index 3 may be expressed as an entire radical by converting the number outside the radical symbol into a radical and then multiplying it by the radicand. Alright, so we did that the previous time. The number outside the radical symbol can be converted by raising it to the power of 3. So exact same thing we did last time, although we were working with an index of 2 before. So 1/2 to the power of 3 is just 1 to the power of 3 over 8, or, well, 2 to the power of 3 is 8. 1 to the power of 3 is just 1, so that would give me 1/8. So 1/8 times, and that's the cube root of 1/8 times the cube root of 160, or the cube root of 1/8 times 160. And if we go 160 times 1 over 8, it goes into 160 20 times. So what we're left with is the cube root of 20. Now, what we want to do for the last examples is just convert our mixed radicals to entire radicals. Alright, so, and for most of these, you should be able to do with a calculator. Sometimes, if you're working with large exponents, that might be a little trickier. But let's take a look at, I'll do every other one here. So, 2 times square root of 3 is equal to, well, this is as an index of 2, which means I raise this 2 to the second power. That would become square root of 4 times square root of 3, or square root of 4 times 3, also square root 12. So every other one, this time I'm raising it to the third power, so this becomes -4 to the power of 3. Right, -4 to the power of 3 is going to give me -4, is cube root of -64 times the cube root of 6, and -64 times 6 is equal to the cube root of 60 -384. And my last one right here, we have to raise 4/5 to the third power. Now, just a little aside here, if you have difficulties with raising fractions to exponents, if I raise a fraction to an exponent 4/5 to the power of 3 or 4/5 cubes, then what you're doing is you're going remember your exponent laws here, but your exponent counts to that 4 as well as the 5. So that's 4 cubed over 5 cubed, or 64 over 125. Alright, so what this ends up being is the cube root of 64 over 125 times 100. We just multiply that straight across. That becomes cube root of 6400 over 125, and we can reduce that by, well, let's see, 25 should go into both of those. So cube root of 256 over 25. Oh, sorry, not 25, 5. And now, without using a calculator, arrange the following mixed radicals in order from greatest to least. Alright, now when we're doing this, sometimes it's easy to, convert them into entire radicals. So this would become 3 squared is 9 times 6 is square root of 54. 36 times 3 is 108, so square root of 108. Square root of 18 we can leave, it's easy to think about like that. 2 squared is 4 times 7 is square root of 28. And 49 times 2, 98, square root of 98. Now we want to think about, okay, well, what's the actual order of these? I know that this is going to be somewhere around 5, right? Like if you just estimate what these values are going to be, I know this one has to be a little over 7 because 7 times 7 is 49, and a little over that you're going to be 54. So somewhere around there. I know this one's going to be close to 10, and this one is just going to be under 10, right? It's going to be 9 something, because 10 times 10 would be 100, not quite at 98. And then this one here would be, close to 4, around 4, which means that we kind of have our order. So from greatest to least, we would go 6 root 3, 7 root 2, so 10, 9, 7, 3 root 6, 2 root 7, and square root of 18.